Hello, everyone. Welcome to today's live broadcast of Improved Evaporation and Concentration for Better Chromatographic Analysis. I'm Meg Evans, the Managing Editor of LCGC North America and your moderator for today's event. We are delighted to bring you this educational web seminar presented by LCGC North America and sponsored by Horizon Technology, Inc. Horizon Technology, Inc. is a leading global manufacturer of automated sample preparation systems for the analysis of organic compounds and oil and grease testing. Understanding the challenges today's laboratories face and the importance of the sample preparation step to the overall analytical process, Horizon Technology helps laboratory managers meet their business objectives by increasing sample throughput, reducing operating costs, and improving the accuracy and consistency of their data. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Submit Questions box located in the lower left-hand corner of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window at any time by clicking on the Enlarge Slides button. The slides will advance automatically throughout the event. If you experience any technical problems viewing or hearing this presentation, please click on the Help button. I would now like to introduce today's speakers. We are very pleased to be joined today by Mark Hamill, Director of International Sales at Horizon Technology, and John Sira, Director of Corporate Sales, Service, and Technical Support at Horizon Technology. John brings a wealth of experience from a previous role as Product and Sales Manager for a major line of extraction and evaporation systems sold by a large life sciences firm. John understands both the technical requirements for sample preparation and the need for efficiency and return on investment that automation can provide. Mark worked for a variety of technical firms before joining Horizon Technology. He brings a depth of fluid handling knowledge and sample preparation understanding to his role. Thank you for joining us today. John, please go ahead and get us started.
Thanks, Meg. So our first slide is on the analytical process. The process begins with sample collection and ends with data handling or data management. We're going to focus on the critical and important step of sample preparation today. Sample preparation is critical because it can lead up to 20% in the variability of analysis, as seen in the quote. There are a number of steps in sample preparation. Typically, we'll see extraction of a sample, cleanup potentially to remove interferences, removal of water or drying of the sample, and ultimately evaporation and concentration of the sample prior to analysis by an analytical instrumentation. This slide is a graphical representation of how Horizon views the sample preparation process, starting with solid phase extraction, moving to drying, and eventually evaporation and concentration. Evaporation and concentration are used in a variety of chemistry lab environments and markets, from forensic toxicology to biotech pharma to environmental analysis and many, many others. The glassware depicted in the slide shows the range of different types of sample collection vessels that may be used in an evaporation process, from very low volume to larger volume vessels that could hold up to 200 mil. It's extremely important. Why sample preparation, evaporation is extremely important in the process of sample preparation. It's because we need to remove solvent or reagent without losing the analytes that you're testing for. There are a number of steps or parameters in a typical evaporation process. Some of the steps may include the use of inert gas, heating of the sample, vapor removal, motion or agitation of the sample, different types of systems, closed systems versus open systems, and solvent recovery. These are some of the items that we'll touch on during the rest of the presentation. So in terms of the different parameters, one of the things that customers or laboratories can do is the do-nothing approach, which is essentially allowing a solvent extract to evaporate on its own, just leaving that in an ambient atmosphere and letting it evaporate. However, this isn't always efficient, it's time-consuming, and it's not very controlled. First evaporation parameter we're going to talk about is inert gas. Gas is used to disrupt the surface equilibrium, which helps to further evaporate solvent, allowing the molecules to escape into the vapor phase. There are different types of actions used to get this process of evaporation started. Sometimes it's a vortex action, which swirls the sample or creates motion. The gas is typically inert gas, such as nitrogen, because we do not want to have analyte oxidation. Next parameter we will discuss is heating. So some of the keys to using heat or heating in an evaporation process is that we need to have ability to heat the sample extract quickly. We want the ability to quickly turn off that heat. We'd like to control the heat to match it with the solvent we're trying to evaporate. And we would ultimately or ideally like to use heat that is uniformly distributed around the vessel that the sample extract is contained in. So there are a number of ways we can use heat in the evaporation process. And in fact, some folks choose not to use heat. You can use hot water or oils, hot plates, hot air, steam, immersion heaters, and even infrared light to apply the heat to expedite the evaporation process. The next parameter we'll talk about is vapor removal. There are typically a couple of ways that vapor is removed from an evaporation system. Some type of high-powered fan, a vacuum, or in some cases there's no vapor removal at all. The reason why vapor removal is critical is to ensure operator safety. Now we'll talk a little bit about motion. As we mentioned earlier, increasing the surface area through motion or through the use of an inert gas to create motion helps facilitate evaporation. Some approaches use rotating or centrifuging the sample to create that motion. Sometimes sparge gas is used to create a turbulence. When we use nitrogen gas or other inert gases, it has the added benefit of a cooling effect, which helps limit sample loss. Next parameter is a comparison between open systems and closed systems. Open systems are typically less complicated evaporation systems, and usually the vapors cannot be efficiently captured, so solvent recovery is oftentimes a challenge. However, open systems provide a lot of versatility in terms of different types of sample vessel or sample glassware that can be used. Closed systems typically use a vacuum and create some type of a seal, either an individual cell or a closed sealed system. This typically allows you to be able to remove the vapors and oftentimes recover solvent. These systems are usually a little less versatile than open systems. Solvent recovery. In today's environmentally conscious world, solvent recovery is increasingly important. Closed systems typically provide the best opportunity to recover solvents or reclaim solvents as the vapor is released from the evaporation system. Solvent recovery is efficient usually when there's large volumes of solvents that are being used in the process. If it's an open system that has a water bath per se and may use an inert gas like nitrogen, sometimes it's difficult to capture those vapors as they come off as the water will come off with the solvent and be very difficult to recapture back into a liquid form. Now I'd like to touch on Kuderna Danish, which is one of the oldest and most common forms of evaporation. This process has been used for many, many years, taught in chemistry classes for all over the world. It is almost an industry standard in a lot of ways. Prior to the advent of automation for evaporation in the late 80s, early 1990s. It typically uses heat in the process. It's usually a closed system or a partially closed system. And one of the benefits with Kuderna Danish is that there's a reflux action involved in the process, that when the solvent begins to condense, the analytes of interest are washed down toward the bottom of the vessel, allowing for better concentration and results. This chart depicts a slide of some of the different types of systems and what they use. Do they use gas? Do they use heat? Do they use vapor removal? So on the left, you'll see Kuderna Danish. You'll see rotary evaporation systems, the ExcelVap evaporator, which is a nitrogen blowdown water bath system, and then the DryVap evaporator, which is a closed cell system. Now I'm going to hand the presentation off to Mark Hamill, and he'll take you through a couple of examples.
Thank you, John. So what we would like to do now is expand upon some of the parameters that John just highlighted that contribute to efficient evaporation. To do this, we're going to cite two relatively modern, new automated products to further illustrate how best to select the evaporation solution for your lab or your application. First, we will highlight water bath nitrogen blowdown systems, and for our presentation we've selected Horizon's ExcelVap evaporator, which is an open system, and we'll discuss how these parameters are applied in the ExcelVap. Secondly, we will discuss closed systems, and for that we've highlighted the DryVap drying and evaporation system, also produced by and sold by Horizon Technology. First, I'd like to highlight some basic information about water bath nitrogen blowdown systems. For our discussion, we'll talk about the ExcelVap, given that we have much familiarity with this product. But there are certainly other similar water bath nitrogen blowdown evaporators that have been available on the market for many, many years. These typically incorporate a heated water bath, typically allow for adjustable nitrogen blowdown, and the ability to accommodate a variety of standard glassware or test tubes currently used in most laboratories. In this case, the system is considered an open evaporator, given that the samples are placed in an open chamber for evaporation to occur. One of the main parameters that we'll highlight of course, is inert gas and how it is delivered to the sample in a nitrogen blowdown system, such as the XLVAP. The key to facilitating and accelerating the evaporation process, as John has mentioned already, involves the creation of motion in the sample during the heating phase of evaporation. By delivering nitrogen blowdown at varying pressures throughout the cycle, a motion is incorporated into the sample, causing more surface area to be exposed and therefore accelerating the evaporation process. A second primary condition is heat. With water bath systems, heat is delivered by heating the water surrounding each of the samples. Water is an ideal conduit for delivering consistent heat to all of the samples at the same time. Additionally, water delivers gentle heating of the sample, avoiding unnecessarily overheating of the sample. Another condition or parameter that is critical to many laboratories is vapor removal. In the case of the XLVAP and other water bath systems, typically an efficient high-powered fan is used to remove solvent vapors during the evaporation process and direct those vapors to a safe area, either to a fume hood or to some other escape area, away from the operators. Vapor removal also facilitates evaporation in terms of removing the solvent from the open chamber. Just to expand upon the parameter of motion and to describe how motion is applied to the sample in nitrogen blowdown systems, we have this diagram which illustrates a nozzle at a specifically designed angle being presented to the sample. The specific angle of the nozzle is critical to creating a vortex action or a circular motion of the sample spinning in the tube. On a molecular level, this motion causes more volatilization of the solvent being evaporated. At the same time, the vortex action washes down the analytes of interest, maintaining good concentration of those analytes into the bottom of the sample tube. Typical water bath evaporators are considered open in that many samples reside in a shared space. Benefits of an open system, as John has already highlighted, are versatility in terms of the glassware that can be used and also the sample volumes that can be accommodated. Convenience in terms of being able to use existing laboratory glassware, and speed. What I mean by speed is that large numbers of samples, as many as 50 or 54 samples, can be evaporated simultaneously. So for high production laboratories who encounter many samples and need to concentrate many samples, an open system allows for multiple samples to be evaporated simultaneously. Water bath solvent recovery is a challenge. This is purely a physics phenomenon. Water is contained in the vapor that is extracted through the fan, and therefore recondensation or condensation of that vapor is very difficult because usually it involves a chilling process. And with so much water content in the vapor that's removed from water bath systems, ice often forms, and therefore solvent recovery or reclamation is often a challenge. Now we will discuss and review how the parameters that we've just reviewed can be applied to closed evaporation systems. And for this purpose, we've identified and chosen to talk a little bit more about the dry vap system, which is a closed system in that it allows for individual control of each sample and delivers vacuum and nitrogen as well as heat as three primary parameters to accelerate the evaporative process. In addition, the dry vap also has a very unique feature in that it can remove residual water prior to the evaporation process. These systems, closed cell systems, have been designed with control of the sample parameters in mind. I mean that you have the ability to control all of the parameters for each sample. And in the case of the dry vap, sample volumes ranging from 50 to 200 milliliters are ideal. Closed cell systems, such as the dry vap, allow for the delivery of an inert gas using a sparge tube. And you can see that highlighted in the slide on your presentation. The use of inert gas in the case of a closed cell system blankets the sample and prevents oxidation from occurring, as well as accelerates the evaporation process. There are three elements to accelerating evaporation with closed cell systems. Typically, delivering heat to the sample is a critical element. On the dry vap, that is accomplished by an immersion heater, which is also silk inert coated so as not to provide an area for analyte retention. Vacuum is delivered to the glass vessel individually. Vacuum allows for the boiling point of the solvent to be lowered dramatically from ambient conditions, further accelerating the evaporative process. Lastly, the parameters at play, both heat and vacuum, contribute to produce a Kuderna Danish-like effect in that during the heating phase of the solvent, a condensation cloud is formed above the liquid phase of the solvent, which contributes to retention of the more volatile analytes, because as they migrate up into the vapor cloud, they hit the cloud, and they're washed back down into the bottom of the concentration chamber. So these three elements work together to efficiently and very quickly evaporate solvents of various types. Individual sample evaporation systems also allow for relatively efficient removal of harmful solvent vapors during the evaporation process. Because each sample is evaporated in an independent chamber, and because vacuum is used typically, it is relatively easy to evacuate the solvent vapors from each of the sample containers and direct those vapors into a capture source of some type or another, or to direct them to a fume hood for proper treatment away from operators in the lab. Motion. We've already learned that motion is a necessary element to expediting the evaporation process. In the case of a closed cell system, such as the dry vap, active and rigorous boiling of the sample occurs to create motion and increase the surface area. In some applications, additional boiling stones can be used to further accelerate the evaporation process. With the dry vap, the sample is never heated beyond its boiling point, which has the added benefit of preserving sensitive analytes of interest. As you've already concluded, the dry vap is a closed system, unlike an open water bath type systems, mainly because samples are contained in individual vessels and they are sealed away from one another. With most closed systems, independent control over each sample is optimized. Recovery of light-end semi-volatile compounds is also optimized. This is mainly due to the Kuderna Danish effect that is developed during the evaporation process. Typically, closed systems also support the ability to accomplish automatic endpoint detection, something that is not typically found in open water bath systems. Endpoint detection allows for the evaporator or the instrument to stop the evaporation process at an appropriate endpoint, which has the added benefit of delivering walkaway capability to those technicians in the lab monitoring the process. And lastly, closed systems offer very efficient vapor removal and potentially solvent recovery. The comparison chart on this next slide highlights for you the differences between a closed and open evaporator system. Some of the highlights, just to recap, for a closed system such as the dry vap are the ability to evaporate, in some cases, directly to a GC vial, the ability to set and control an endpoint for evaporation to stop at a particular volume that's desirable, perhaps 1 milliliter or less. And also, one of the added benefits of a closed system is the ability to recover vapor easily and efficiently during the evaporation phase. For open systems, some key highlights that might factor into your decision are compatibility with most glassware. Also, if you're a high production facility, you might be interested in being able to process as many as 54 samples simultaneously. However, with water bath systems, recovery of the evaporated solvent will be very difficult due to the water content in the exhausted vapor. So, how to choose the right evaporator for your facility and your application. Certainly there are some well-founded, tried and true methods, such as Kuderna Danish, which typically handle one sample at once and are relatively slow. Rotary evaporators are quite common and available, but typically handle one sample at a time. Water bath systems or open nitrogen blowdown systems such as the XLVAP offer convenience and speed. Closed cell systems such as DryVap offer optimal control over the conditions applied to each sample. So some considerations that lab managers and lab owners must factor in are the volume of sample to be evaporated, or the volume of sample extract to be evaporated, the total number of samples that must be accommodated in a weekly or monthly capacity, the types of samples being evaporated. For those more volatile semi-volatile analytes, perhaps a closed cell system would deliver higher recoveries than an open cell system. And of course, all of this must be weighed against the total cost and investment for hardware to evaporate precious sample solvents. We're nearing the end of the presentation, and what we have tried to do in this next slide is give a few real-world examples for how lab managers in the past have made their selection process based on purchasing an open or closed evaporative system. In the first example, a clinical laboratory who may be preparing samples for LC-MS analysis and who generate sample extracts somewhere between 5 and 7 milliliters, and who need to reduce that volume to dryness, would typically select a water bath nitrogen blowdown system like the XLVAP, where samples could be contained in common glassware such as 13 by 100 millimeter test tubes or others, where they could evaporate many samples at one time and keep their LC-MS analytical devices running as much as possible. For medium to small environmental laboratories, however, where samples are prepared manually using LLE, and where there are a small to medium number of samples being prepared weekly, they may need to dry and evaporate larger volumes of sample, somewhere between 180 and 200 milliliters, for example, of DCM, and then analyze those evaporated samples through GCMS analysis. The dry VAP system, or a closed cell system, might be the perfect choice for this lab, where 1 to 6 samples could be dried and concentrated simultaneously for analysis every 30 to 40 minutes. The same lab above may use solid phase extraction rather than liquid-liquid extraction to prepare samples. And therefore, they may have smaller volumes to evaporate, or they may also still continue to use liquid-liquid extraction and also have larger volumes to deal with. The XLVAP would allow for samples of large and small volumes to be accommodated in an open cell system, simply because interchangeable racks supporting different glassware can be used with the XLVAP and accommodate large volume samples up to 200 milliliters and smaller volume samples, assuming that drying can be processed offline before evaporation. So in conclusion, what we hope we have communicated to you in this presentation is that sample preparation is a key step in the analysis process, regardless of how the samples are prepared or the nature of the sample. Evaporation is a critical step in the sample preparation process, as it affects both the analytical performance and the laboratory's productivity. Improvements in matching your sample to the evaporative device and its characteristics will help you reduce variability while improving recoveries for your analytes. Examples for choosing a system based on sample volume, the type of analytes, the sample demand, and your financial capabilities hopefully have been communicated to you so as you can make a more informed decision that includes analytical and business components. This concludes our presentation today. I'd like to thank you all very much for participating. And Meg, I'd like to hand it back to you at this point.
Thank you both for that informative presentation. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. As a reminder, text chat is located in the lower left-hand side of your screen. To submit a question, type your questions in the small text box in the lower left-hand side, and when finished, click the Submit button. We will answer as many questions as we can. Now let's move into the live question and answer portion of the webcast. Our first question is the purge gas generated in the lab or supplied by a connected cylinder?
The gas typically can come from a number of sources. Many labs have house gas, which is a direct connection to a large tank of gas that may be sitting outside the facility. Canisters, nitrogen tanks oftentimes can be used. And more recently, we've seen an increase in nitrogen gas generation devices.
Okay, the next question is, how is the heater cleaned between samples on the dry vap?
This is Mark. The dry vap has a feature that allows for automatic or manual rinsing of the entire inside surface of the heating vessel or the evaporation chamber. So a solvent can be used to deliver rinsing action to the entire internal components, including the heater coil and the sparge tube. And that can be programmed either manually or automatically to occur.
With the Excelvap in the water bath, is water condensing in the sample an issue?
We don't usually see water condensation in the sample as an issue. When the nitrogen is blowing down in a vortex fashion, it's basically keeping anything from getting into that individual sample vessel that's in the water bath. So the fan is pretty powerful, and it's drawing out any of the liquid, any of the water that's turning into, that's condensing. It's drawing it out through the fan, and the nitrogen is drying that sample down. It's also creating a blanket or a layer over that extract as it dries down, keeping condensation from getting in there.
How do I recover solvent from a closed system? Do you offer anything?
Horizon has a product we call the reclaimer, and this is a device that can be connected to a closed cell system, such as the dry vap or a rotary vap system, where all of the vapor, solvent vapor that's exhausted during the evaporation process can pass through a cooling element and condensed into liquid form and contained in a solvent bottle. So yes, we offer a product called the reclaimer that can be used to recover solvent from the evaporator.
Why do I care if a system is open or closed?
It comes down to a choice for the type of analysis that the lab is performing. And as Mark pointed out, closed cell systems give you a lot of control and also can typically give you an opportunity to recover solvent. That's very important to some labs. Open systems are oftentimes less complicated, which typically means less expensive, and they also provide more flexibility or variability of glassware that can be used, which may be more functional for a different laboratory. So it becomes a choice, really, of what type of analysis the lab is looking to perform and which instrument best suits that lab.
How do you prevent samples filled to the top from splashing?
In the case of the Excelvap water bath nitrogen blowdown system, that issue is dealt with in several different ways. With some of the older systems that are available today on the market, the operator has to control the pressure, the starting pressure of the nitrogen being blown into the sample tube So typically they'll start at a very low pressure, but as the solvent moves down or evaporates in the sample tube, the operator would typically walk over to the evaporator and increase via a manual knob the pressure being allowed to blow down through each of the nozzles. In the case of the XLVAP, which is a much newer and recently developed product, that process is controllable by software. So with the XLVAP, you can set a starting pressure for nitrogen, which might be very gentle. And during the evaporation process, if it's set for 30 minutes or 40 minutes, the nitrogen pressure that's delivered to the sample will increase incrementally throughout the run, so that splashing is avoided initially when the samples are full, but evaporation is optimized because more nitrogen is being delivered as the sample migrates down into the sample vessel.
How do you get XLVAP nozzles to go from 6 tubes to 40 tubes?
The XLVAP has been designed with a manifold nozzle array or a gas nozzle array that can accommodate up to 54 positions. So we have the ability to configure that manifold for a number of different types of racks. So our lower volume racks, our 13 by 100 type test tube racks, can accommodate up to 54 positions. Our larger volume racks can accommodate up to 6 positions, and it's a quick connect nozzle, so the nozzles are twisted in and twisted out and configured appropriately with the rack and the glassware of choice.
How do I know what the optimal temperature setting on the dry vap is for a given solvent?
Fortunately, with the advancements in technology, the dry vap has been designed so that you don't need to set a temperature. In fact, with the dry vap, we don't allow you to set a temperature. Instead, the system brings the solvent to its boiling point, and it stops delivering heat to the heater. So we get the sample under vacuum to begin boiling, and we stop delivering heat. This has the added benefit of preserving very sensitive analytes and not overheating the sample.
How many steps can be programmed into the XLVAP pressure program?
The pressure program is essentially a one-step program. We can set an initial starting pressure and then an ending pressure. And there are a number of ways we can do this over the entire length of the evaporation, starting, say, at 6 psi and ending at 24 psi over the course of 30-minute evaporation time. Or we can set a 6 psi to 24 psi over 10 minutes and then set a constant pressure for the remaining time of, say, 24 psi for the remaining time of the evaporation process. It's a starting and end point or a static pressure.
Is dry vap an option to concentrate perfume extracts at trace level to be measured by GCMS?
I guess the answer to that question is maybe. We would need to understand the analytes of interest first, and we would certainly love to discuss that application in more detail after this presentation.
Okay. Can either of your systems handle corrosive solvents such as diethylamine or hydrochloric acid?
I guess the answer to that one is maybe, but for the most part, these systems are designed for organic solvents. So I think we need to deal with that question also offline and consult with our on-staff chemists.
Okay. How does the closed system determine the final volume and stop evaporation, i.e. 1 milliliter final volume?
This can be accomplished in a variety of different ways. However, on the dry vap system, the concentrator tube has a very unique shape. It's a large chamber followed by a small tip, which typically contains about 1 milliliter of volume. And that tip resides in a chamber where an infrared sensor monitors the meniscus level, so that as the solvent evaporation occurs and the meniscus moves down, the infrared sensor can see where that meniscus is, and we can adjust the volume where the sensor will see the final volume in the tip. So we can control an endpoint volume from 1 mil to 0.9 mil to 0.7 mil, all the way down to perhaps 0.2 milliliters.
Can Horizon make custom racks for the ExcelVap so that we can use 200 milliliter tubes currently used in our TurboVaps?
So the answer is a yes and a no. And the yes is we can make custom racks. And why I say no is that the current TurboVap tubes are longer, so our limitations are longer or longer than our bath would provide. So the limitation really is the depth of the bath. And if the bath and our rack can accommodate a particular type of glassware, we can definitely work out a custom solution. But with the current TurboVap 2, number 2 tubes, those tubes are a little longer and narrower than our system can accommodate. We've developed our own glassware, and one of the big benefits of the glassware that we are marketing with the ExcelVap for 200 mil is that it's specially designed such that the evaporation process virtually comes to a halt when the sample is evaporated to the 1 mil point. It has to do with the design of the instrument and the design of the glassware. So this really prevents sample loss.
Will additional rinses help in recovery?
It depends on the analytes of interest. For more robust analytes, those with higher carbon content, they tend to recover very easily. But for more volatile compounds, lighter end compounds, rinsing can positively impact recovery. So in many of the application notes that are available from Horizon, we will make recommendations on rinsing or not rinsing to improve recoveries if necessary. So in some cases, yes. In other cases, no.
Is it useful to use an internal standard for recovery testing?
Oftentimes we see the use of internal standards to validate or verify recovery testing. So I think that's pretty common practice that we see in our customers' laboratories.
Does the ExcelVap come with pre-programmed methods based on solvent use and volume?
We don't have the ability to store programs in memory on the ExcelVap. You're always in live run mode. However, we do have some support material, charts and figures, which serve as a guideline, which identify the type of tube, the type of solvent, and how much time you should allow for evaporation depending on the pressure being delivered. John?
Oftentimes we also will see customers perform kind of their own method development. And what we see is once they've developed the method, how they're going to use it, that method can remain pretty consistent with consistency of results. So method development is sometimes important for labs as they're adding a new instrument.
For slightly soluble solvents like DCM, doesn't the solvent contaminate the water in the bath?
Typically not, because it is pulled out through, in the ExcelVap, it's pulled out through the fans from a vapor. And one of the things that we've done to ensure that we do not contaminate the bath is that we built a drain into our system that is pretty unique for water baths. So once you're finished for the day, you can quick connect a drain line and evacuate all of that water from the chamber. So if you do have a spill, can quickly remove the water.
Okay. What is the advantage of a dry evaporator over a parallel evaporator or rotary evaporator that can do multiple samples?
I think the answer there is control. With the dry evap, there's a capacity to handle 6 samples at the same time. And of course, all of those samples could be processed with the same parameters, but what we see more likely or more commonly is that people will be performing a specific evaporation on station number 1, for example, with a certain solvent, and running perhaps a second sample with a different solvent on station number 2. And in each case, the parameters of control, heat, vacuum, and nitrogen, can be controlled and delivered uniquely to each one of those 6 stations. So not all samples have to be treated the same on the dry evap.
Is it possible to evaporate environmental samples to 0.5 ml, or is 1 ml more realistic?
0.5 ml is realistic. We can definitely, we've seen that and we've done that work in the dry evap, and we can also get pretty close to 0.5 ml in the Excel evap. So it's really working with the particular sample extract and seeing what pressure might work, what heat might work to get you there.
Oftentimes with low volume evaporation going down to 0.5 ml or lower, the challenge is always maintaining good recoveries. The longer you evaporate a sample, the more likely you are to lose analytes of interest. So it's a delicate balance, getting the concentration that you want, but also not losing the analytes in the process.
How should one go about performing additional rinses?
In the case of the dry evap, if the device has been configured with a rinse solvent, it's as simple as pressing a button. So once the evaporation cycle or the heating cycle has occurred, it's very easy to simply press a rinse button and deliver a predetermined amount of rinse solvent to the internal vessel on the dry evap. Additionally, manual rinsing could be accommodated or could be performed by using a pipette and delivering a programmed amount of solvent to the various surfaces that you wish to rinse.
In water bath systems, oftentimes people will use a squeeze bottle and individually rinse the sample vessels as the evaporation gets near to an end. And that is, again, as Mark said in an earlier statement, it's dependent upon the recoveries and what type of analytes you're trying to recover. If they are very sensitive analytes, volatile analytes, you may need to rinse. But I think through the method development process, the individual lab can determine whether or not additional rinses or manual rinses will be necessary.
On the dry evap system, can you explain the setup of the inline solvent extract drying?
Yes. Dry evap has a very unique feature in that using a technology we call dry disk, a technician can essentially pour their extract coming from liquid-liquid or solid phase extraction techniques. And typically that extract will contain some residual water. So you might have 50 milliliters, you might have 100 milliliters of solvent with your analytes in the solvent and an additional amount of residual water. By pouring that into a glass vessel where the dry disk resides, the solvent will be allowed to pass through the dry disk membrane, whereas any residual water will be trapped above the membrane. So all of the solvent will be pulled into the evaporation tube, but any residual water will remain behind. And this has the added benefit of allowing the operator to deal with or re-extract that small residual water if necessary, rather than drying it using sodium sulfate and never being able to recover it or reuse it again.
The water is actually physically separated from the analyte, and when the vacuum is from the solvent extract containing the analyte. So when the vacuum is applied, it's almost instantaneously pulled through. We also offer that technique in a more manual fashion for people who would want to use that with a water bath type system like the ExcelVap. We have disposable dry disc technology and dry disc technology that can be connected to a ring stand.
Can you please explain again why sample loss due to evaporation to dryness is unlikely in the ExcelVap?
So how, when in the dry vap, in the ExcelVap, when we use the technique of nitrogen blowdown in a vortex manner and vortex shearing, basically works to wash the sides of that tube down in a circular motion so that any analytes that get stuck to the tube are slowly but surely concentrated down as the solvent comes further and further toward the bottom of the tube. So as we're bringing that to dryness, we've got a gentle heat applied. We've got gas flowing on top, effectively keeping as many of the analytes of interest as possible in that tube. The vortex technique washes the sides of that tube down, and ultimately you'll have a dry tube with the residual analytes of interest in the tube. So this is a common technique. It's been used for a long time. The combination of the gentle heat and the nitrogen does a really good job at limiting analyte loss.
Okay, thank you, Mark and John, for those insightful answers and for your presentation today. Unfortunately, we're out of time. I want to thank the audience for your interesting questions and participation in today's event. I would also like to thank our sponsor, Horizon Technology, for making today's educational webcast possible. Please note this webcast will be available for on-demand viewing through June of 2014. You will receive an email from LCGC alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time. Goodbye.